Okay, welcome to notation for differentiation. So, a lot of people would wonder, why is it so important to make sure that our notation is correct? Well, much like when we speak, our grammar has to be correct. When we're doing English and we're writing our essays, we've got to have correct grammar, we've got to have great structure for our similes, and so on. We've got to make sure our paragraphs are great so that we can actually communicate what we are wanting to say to someone else. And we've got two main ways of communicating that we've differentiated, or that we've got some kind of gradient function instead of the original function. We've got Leibniz and we've got Newtonian notation. So, by Newton notation, we can have some function, we could call it f, and our main variable could be x. Or we could have some function g, and our main variable is t. Now, when we differentiate these, we just basically add a dash. So f of x becomes f dashed of x. Now, this is important not to just write it as f of x again, because if f of x is, for example, 3x squared, when we differentiate this, it would be 6x. Now, these two are not equal. These two are not equal. So there's no way that we should be missing out our dash up here, because they are not the same. So f of x goes to f dashed of x. Similarly, when we do g of t, we do not write g dashed of x just because we're used to working with x's. We need to say g of t. Okay? Because t is our main variable that we're using, and g is what we've called that function. Now, this is Newtonian notation. If we were to differentiate again, which we do in kinematics, we could easily say f double dashed of x, or g double dashed of t. Okay? Cool. Now, if we were going to do Leibniz notation, where we have just y and then we don't actually state what our variables are, this would go to dy d whatever we are differentiating with respect to. So, for example, if we're differentiating with respect to x, it would become dy dx. Like above here, we've got 3x squared. If we had y was equal to 3x squared, then we would have dy dx, because that's our main variable that we're differentiating with respect to. So that's why we would have x underneath here. Okay? Or later on, we'll come to kinematics, when we've got our displacement, S for displacement. We would that when we differentiate displacement, we would get velocity, but velocity is also equal to ds dt, because we are integrating with respect to t. And again, when we come to kinematics, you'll find that when we differentiate velocity itself, it would go to acceleration, and so acceleration would be the same as dv dt. Now, because velocity is the same as ds dt, acceleration is also equal to d squared v over, d squared s over dt squared. Okay, now this is, so try not to get too confused at the moment. I know that's a big ask, but here we've got our second, so here we've differentiated once, here we have differentiated twice. Up here we have differentiated once and we've just had one dash. Here we've differentiated twice and we've got two dashes. Down here we've differentiated the once and we've got one d up top and we've got d and what our main variable is at the bottom. So the second time we've differentiated, notice that we've got powers here. So our powers change. Okay, so that's how you can tell how many times it's been differentiated from the original function. Cool. Thanks for watching.